Hey everyone, welcome back to physics. This will be lecture 18 of the course. And in this section and the sections to follow, we're going to zoom in on Newton's laws and look at specific problem types that may be more challenging than the examples we've seen, that take specific advantage of the principles that we've laid out of Newton's. And so in this first section, we're going to zoom in on Newton's first law and study problem types where we're dealing with particles that are in equilibrium. So let's go ahead and jump into it. We'll call this section 4.1, using Newton's first law, particles in equilibrium. So we're going to go ahead and work some problem types in this section that involve bodies in equilibrium, and we'll do three specific examples, and each of them will make explicit use of Newton's first law. And so let's recall that a body in equilibrium will remain in equilibrium unless acted upon by a net force. That would be a restating of Newton's first law. A body in equilibrium will remain in equilibrium unless acted upon by a net force. Right? So there's many ways to state Newton's first law. That's one way. Okay. And so mathematically, we know what that means is that if we sum all the forces acting on a body, and the body's in equilibrium, then all of those forces acting on it will equal 0. Okay? And so that's really the key to the coming three problems. So let's start with the hanging gymnast problem. So a gymnast with mass m equals 50 kilograms suspends herself from the lower end of a hanging rope. Suspends herself from the lower end of a hanging rope. Okay? And she is perfectly still. Right, meaning she's not swinging, not moving up or down in any way. She's perfectly still at the bottom of this hanging rope. And so, we'll draw a picture. Hardly really need one, but it's good practice whenever you're doing this kind of thing to just draw some sort of a picture. Okay, so you've got the rope, and then you've got the gymnast hanging at the bottom of the rope. In this case, we're just going to draw a circle. There's a couple questions. So, what is her weight? And what's her weight? Right, remember that's the force that gravity exerts. What force does the rope exert on her? Okay, what force does the rope exert on her? And the third question, what is the tension at the top of the rope? Okay, so three questions really, and then these, again, this is a sort of an introductory kind of problem, just to get us familiar with the general flow of problems like this, equilibrium problems. All right, so the first thing you really want to do is draw a picture, which we've done here. We've got the rope and the gymnast. Now, in some cases like this, maybe you could skip the picture and go straight to the free body diagram, but in general, you just want to draw a picture, make sure you understand physically what's being described. And in some problems, some that we'll do in a moment, the picture is very helpful. Helps you really kind of visualize what's happening. But let's go ahead and draw a free body diagram. Now, usually what you want to do in the case of equilibrium problems like this is you really want to have a free body diagram for all the different bodies involved. And sometimes all the different bodies can be treated as one body, sometimes they can't. In this case, we'll treat the two bodies as separate. So we've got the gymnast, and then we've also got the rope. All right, so let's just kind of think of them as separate. Again, there are different ways to run this problem, certainly faster, more efficient ways. We're focused on just like laying out all of the different ideas about the problem solving, not necessarily doing it the fastest way possible. All right, so we'll start with the gymnast. We've got the gymnast here, and the forces acting on the gymnast are the force of gravity. So you got the weight of the gymnast, which is the mass times the gravitational acceleration. And then you've got the rope, the tension of the rope on the gymnast. So we'll label it like this, the rope acting on the gymnast. Okay, and they're equal and opposite because the gymnast is perfectly at rest, right? Just hanging motionless at the bottom of the rope. Okay, now separately, you've got the rope, right? So the rope has, it's under tension, right? So there's a force pulling down on the rope, and that force would be what? Well, it's going to be the tension of the girl on the rope, right? Or the gymnast on the rope. Right? So the gymnast is pulling down on, hanging from it, in fact. And then the rope is under tension on the other end, and we'll just say that's the tension that the ceiling applies to the rope, right? So it's fastened to the top of the ceiling. Okay. Now, an important thing to notice here is that really the tension, the force that's acting, the tension that is caused by the rope on the gymnast, this force here, is really connected to this force, isn't it? Right? This is a third law action-reaction pair here, isn't it? Right? So the rope acts on the gymnast and the gymnast acts on the rope. Right? So these two are kind of connected. So whatever the value of this force is, then this one can be derived by just recognizing that this is a action-reaction pair. Okay? And so here are the free body diagrams in play. And so given this information and the fact that, a little bit of information in the problem, we can figure out each of these questions. So let's start with one. What's the weight of the gymnast? Well, her weight is just the magnitude of the force of gravity, right? So you've got the mass of the gymnast times gravitational acceleration, and so that is what, 50 kilograms times 9.8 meters per second squared, and so 980 divided by 2, so 490 newtons. All right, so that's the force, that's the weight of the gymnast. Okay, so that's the first question. The second question says, what force does the rope exert on the gymnast? Well, what we just discovered was this force here, right? So this is equal to, we'll say negative 490 newtons, because we'll make the axis positive up, negative down. So negative 490 newtons here. And so question 2 is, what force does the rope exert on the gymnast? And that's this force, isn't it? So this force is equal but opposite of the gymnast's weight. It's holding her up specifically. So we'll say that the force of the rope on the gymnast is equal to, well, it's equal and opposite of W. So it's equal to negative W, isn't it? Which we'll say is 490 newtons. All right. Okay. So this force is in the opposite direction as the force of gravity, and that's why the sign flips. So, sorry, this one was negative. Yeah. Well, that's the magnitude. That's fine. Okay. And then, then the third question is, what is the tension at the top of the rope? So now we're over here. What is this guy? Well, this guy here and this guy here, an action-reaction pair. If this is 490 newtons, then this must be equal to negative 490 newtons, right? Pulling down on the rope. And the rope is in equilibrium, right? The rope is in equilibrium. Right, so the implication is then that the sum of these two forces must be equal to 0. So what does that mean? This force has to be here. Well, that means that the tension in the of the sealing on the rope, the force of the sealing acting on the rope, must be equal to 490 newtons as well. Okay. So this is a simple example, but it's an example that shows, kind of the process, right? You start with just a picture of the situation, and then you break down the bodies involved, and you generate free body diagrams, just the forces acting on the individual bodies. And then where helpful, you can connect the forces causally like this. Say, well, this force here is an action-reaction pair with this force, and so whatever this value is, this force will be opposite and equal to that, right? And so you can kind of link free body diagrams through this these action-reaction pairs. So it's just kind of a simple problem, but a good one to start with, just giving you the lay of the land for solving these types of things. All right, very good. Let's jump to another example. And so this example is going to have a little bit more complex free body diagram. And we'll say, okay, so this one is going to be a heavy object, hangs from a chain, that is linked to an, we'll call it an O-ring, and I'll draw a picture in a second. You'll get the idea here. So a heavy object hangs from a chain that is linked to an O-ring and then two other chains. Okay, so I'll write the rest of the problem out, but let's visualize this for a second here. So I've got the ceiling and I've got the wall. All right, and I've got some heavy object here. All right, and it's connected to a chain, right? And the chain is connected to an O-ring. And that O-ring connects the two other chains. And so one is fastened to the wall. One is fastened to the wall like this, and the other is fastened to the ceiling. So the other is fastened to the ceiling at a 60-degree angle. Okay, and so basically like this, and then we'll say this is 60 degrees. Okay, so you've got the chain kind of pulling down. It's pulling this kind of at an angle, and this one is horizontal. If the mass of the object is 100 kilograms, what is the tension in each of the chains? Okay, so a little more involved here. The picture has to be drawn to kind of understand. This is the ceiling right up here. And this is the wall over here. Right, and then you've got just this big heavy object, 100 kilogram object. So let's think about the weight first. So we're going to generate two free body. We're going to think of the free body diagram of the weight, the object here, and then secondarily the O-ring. Now clearly everything is in equilibrium. There's no acceleration, nothing's moving. There's just suspension here, right? So let's consider the object first. Okay, and so that's a real simple, you got the 100 kilogram object, and it's got a force of gravity pulling it down, and the chain has some kind of a tension, which we'll label tension 1. So you got tension 1 here, and then we'll call these others as well. So you got 3 chains involved. So the first one, the force, we're going to call tension 1. Okay, and so we can calculate these things really easily. The magnitude of the weight here is going to be equal to the mass times the magnitude of gravitational acceleration. And what we see there is 100 kilograms times 9.8 meters per second squared, so 980 newtons, right? So this is equal to 980 newtons. Okay, because the weight's in equilibrium, we know from Newton's first law, right? Newton's first law tells us that the magnitude of the force pulling up on the weight is equal to the magnitude of the weight, right? And so the implication there is that T1 is equal to, well, the magnitude anyway is 980 newtons. Okay. So let's make positive up, negative down. So we'll put this at negative. All right, very good. Okay, and so that's kind of what's going on with the object, the hanging object. Now let's look at the O-ring. So next, let's look at the O-ring. Okay, so what's happening there? Well, so we'll start by just redrawing it here. We've got this ring, and we've got a force down, T1, and that's equal to, we just said, negative 980 newtons. And then we've got this thing here, which we'll call, well, we've got 2 others. We'll call this one T2, and we'll call this one up here T3. All right, so you've got these 3 forces kind of operating on the ring. Now, the way you'd want to deal with these, because these are not, so it's very important to coordinatize the problem, right? We always have to think about, when we're talking about equilibrium problems, we always have to, physics problems in general, we always have to figure out some kind of a coordinate system. So in this case, the coordinate system that you'd probably want to use is to imagine the x-axis horizontal and the y-axis horizontal or vertical, right? Like so. All right, so you've got your x-axis and you've got your y-axis. And now obviously tension 1 is along the y-axis, tension 2 is along the x-axis, but you've got tension 3 here that's kind of in between, right? And so to solve equilibrium problems like this, we need to know the x and y directions of all the forces. So basically, we need to break down this tension 3. Now we know that it makes a 60-degree angle with the ceiling, and so the implication is then that this would be a 60-degree angle as well. Okay, and you can just think about the geometry of that, and it's pretty straightforward. And so we can think through what a triangle would do here, what a triangle would look like. So if you got 60 degrees here, and this is T3, and we'll just say this is X and this is Y. And this is an exercise that you'll get very good at if you do homework problems. Well, basically, what we could say is that the sine of 60 degrees is equal to y, the opposite side, over T3, the hypotenuse. And so that means y is equal to T3 times the sine of 60 degrees. And the cosine of 60 degrees is equal to x over T3, and so x equals T3 cos 60, right? And so we could redraw this and include this information. Okay, so we've got the O-ring, we've got T1 equals negative 980 newtons, and then we've got this force coming out the top, and then we've got a force coming out both sides. Now the force coming out the left-hand side, that's just T2. But the force coming out the top, this is T3 times the sine of 60 degrees. The force coming out the right-hand side is T3 times cosine of 60 degrees. Because remember, T3 kind of goes right in the middle. Right, so we've taken the tension that's coming, that's off axis, and we've broken it down into its component parts. So part of it's on the x-axis, part of it acts along the y-axis. Right, so in doing that, we can solve the equilibrium problem very easily. So we can now establish a system of equations. Right, we can set up a system of equations. We need to know what T2 and T3 is, right? And so we could set up a system. So the sum of the forces in the x direction are, well, we've got this T3 cos 60. And then we've got T2 minus whatever T2 happens to be. And those need to equal 0. And then the sum of the forces in the y direction, well, you've got negative T1. I'm just going to put plus here, and we'll leave everything as written. So you've got T1 plus this guy up here, right? So you got this one and this one. So plus T3 sine 60 degrees. And that has to equal 0 as well. Everything's in equilibrium, so the forces have to offset each other perfectly. And then T3 can obviously be found from the second equation because we know what T1 is. We were able to identify that one, right? And so the sum of the forces acting in the y direction will be equal to negative 980 newtons plus T3 times sine of 60 degrees, and that's going to equal 0. Right, and so T3 is going to be equal to 980 newtons divided by sine of 60 degrees. Okay, and that's 980 newtons divided by about 0.866. Okay, and so when you run all of that through a calculator, you get 1,132 approximately newtons. So that's T3. Okay, so T3 must be equal to that. And we could have, I mean, we'll see that this is consistent if we plug it into this other expression as well, right? But from this, we can calculate T2 sort of simply because we now know T3. So the sum of the forces in the x direction are equal to 1,000, well, let's write them out first. So it would be T3 cos 60 degrees plus T2, and that is equal 0. And so T3 is 1,132 newtons times the cosine of 60 degrees plus T2, and that has to equal 0. And so T2 will be equal to 1,132 newtons times the cosine of, and so we're just saying the magnitude here, times the cosine of 60 degrees. And so this is 1/2. Cosine of 60 degrees is 1/2, and so that would be made, that we just have to divide this by 2, so 566 newtons. Okay, and so now tension 1 is, putting the signs on, negative 980 newtons. It's in the down direction. Tension 2, right, that's this one. It's also in the negative direction. We'll say negative 566 newtons. And tension 3, that's positive, is 1,132 newtons. Okay, and so there you go. There's the tension in the 3 ropes. Okay, and so it's remarkable. I mean, I'm sure you've seen this before, but it's always remarkable to me to see how, you know, if you've ever taken trigonometry and you just thought you were just messing with triangles, it was all rather arbitrary. But to just see this kind of thing and to realize that this is in fact how nature works, forces will break down by the ratios of triangles' legs. It's just quite remarkable. It's very fascinating. And it just shows you that the universe is clearly orderly. It is clearly an organized and mathematical, right? Very, very nice. Very nice little problem. Okay. We'll do one more problem, which is a little more complicated yet. Not too bad by any means, but these are just 3 examples of solving problems in equilibrium. And so this one will say a large block, this is a classic problem also from Newton's first law of classic problem. A large block is pulled up a 15-degree slope. So a large block is pulled up a 15-degree slope, and it's pulled up by a falling weight attached to the block over a pulley system. Attached to the block over a pulley system. Okay, so let's draw a picture here. What are we talking about? Well, we've got some kind of a ledge like this, and we've got some kind of an incline, and we're told that it's 15 degrees, right? And so then we've got, you know, maybe some kind of a pulley system here at the end. And then we've got this block on this ledge, or sorry, on this incline. And it's being pulled up the incline by a weight that is hanging from this rope through this pulley, right? And so this guy here is pulling down, and as it pulls down, it pulls the rope, and the rope naturally kind of pulls the block up this incline. Okay. So here's the question. If the block's mass is 1,000 kilograms, that's this thing, 1000. If the block's mass is 1,000 kilograms, how much mass is needed to drag the block up the incline at a constant velocity? Okay, that's the question. So we're told that this block is on this incline. It's being dragged up through the mechanism of this weight through this pulley. And the question is, how much mass, what's the mass of this thing here, need to be in order to have the system be in equilibrium? Now, it does say that the block is moving up the incline, but it says that it's moving with constant velocity, which means it's in equilibrium, right? It's not accelerating. Okay. And for simplicity's sake, we'll just say that there's no friction either on the pulley or between the block and the incline. Now, you could solve the problem by making some assumptions about the pulley and the incline, of course, but for this example, we won't. We'll just assume frictionless surface and frictionless pulley, perfect ideal pulley. All right, so let's consider the free body diagrams here. We're obviously going to have 2 of them. We've got the block, and then we've got the weight. Okay, and so let's start with the block. All right, it's the one that's a little more complex. All right, so I'm going to kind of draw it as it would appear in the problem. You've got this 1,000-kilogram block on this incline, so it kind of is oriented like something like this. And it's being pulled down naturally. It has a weight, and we'll denote it as W sub B, which will be equal to the mass of the block times the gravitational acceleration. Okay, and the other thing we have for sure is the normal force between the incline and the block, and so that's the normal force. All right, so remember the normal force is going to be angled somewhat, right? In this case, the normal force isn't going to, it's always perpendicular to the surface that the object is resting on, and so the object is on this 15-degree incline, and so the normal force will be acting in a direction not quite the same as the gravitational acceleration. And then we've got the rope that's attached to it pulling it up the incline. Okay, and so these are the 3 forces that are acting on the block. Okay, and then secondarily in the problem we've got this weight. Okay, and we'll just denote it here. We've got this object which has some unknown mass, which we really need to figure out. And obviously you've got gravity pulling this thing down, and so that's equal to mg. And then you've got the tension in the rope holding it up. Right? Remember, there's a rope that connects these two, so we can think of an action-reaction pair here between the two. There's some kind of a connection. Whatever this force is, this one is equal but opposite. Okay? So the two bodies here, the block and the weight, are linked through the tension in the rope. They really move in the same they accelerate in the same way. There's, we could treat the rope as being having no mass, negligible. So let's start by looking closer at the three-body diagram or free body diagram for the block. So the weight of the block is what? We can figure this weight out here. So W sub B, let's take the magnitude, is equal to M times G, MB times G, which we're told the thing has a mass of 1,000 kilograms. Nice round number. And it's multiplied by 9.8 meters per second squared, and so we get 9,800 newtons. Kind of a heavy block. Okay. Now, when we look at this free body diagram, there's actually a force at work here that we haven't quite captured. I mean, we sort of have captured it, but we haven't quite got it, all of the details out. So we need to look a little bit closer. Right, so we've got, I'm going to redraw it here. I'm going to redraw it, and we're going to take a look at this. So I've got the 9,800 Newton force pulling it down. Okay, I've got the tension here. And I've got the normal force in this direction. Okay. Now, the technically, like, the block is on an incline, right? If the rope is cut, you can imagine the block will slide down, right? So there's some force kind of operating off the back side of this thing. And what is that force? Well, that force is related to this gravitational force here, right? So technically, this 9,800 newtons in the down direction, the weight of the object, has an x and a y component. So it really needs to be broken up separately. Right, so this would be, so if this is 15 degrees here and this would form a right angle there, then that must be 15 degrees. Right, so we're dealing with this triangle here, and we know that this is 9,800 newtons here. Okay, at this point we really need to settle up on some kind of a coordinatization. And I'm just going to do it this way. I'm going to extend this one and make this the y-axis. It doesn't matter. It's just notation. But and I'm going to make that the x-axis. Okay. And so the side adjacent to the 15 degrees is y. It's along the... sorry, it's actually... yeah. Well, we'll do it like this. Y and x. Okay, and this is a right angle. And so what is x here? Well, x is going to be equal to 9,800 newtons times the sine of 15 degrees. And y is equal to 9,800 newtons times the cosine of 15 degrees. All right, just doing that trig that we've done a couple times already. Okay, so then we can figure these numbers out. So x is equal to, if you do sine of 15 degrees times 9,800 newtons, you should get something like 2,536 newtons. And for y, when you take 9,800 times cos 15, you should get 9,465 newtons. Okay. So what we can do is we can just kind of redraw this thing now with all of the forces coordinatized, like along the x and y axes. Right, so I'm going to redraw it one more time, and you really wouldn't have to redraw it this many times. I'm just kind of trying to walk through the thinking on a problem like this. So in the down direction, right, that's this side here, we're going to have 9,000. Oh, I think I have this backwards. I want that to be x, and I want that to be y. So this guy here is opposite the normal force, and so that's going to be the 9,465 newtons, and then the normal force is going to offset that perfectly with the same thing, so 9,465 newtons. And then you've got the tension in the rope, which is unknown. All right, we haven't ventured over to the other body yet. We haven't gone over to the weight yet. And then this piece here that's pulling it down the incline, this piece here, that force is what? Well, that's this one, 2,500. That's this guy here. This leg of the triangle is pulling it like that. And so that's 2,536 newtons. Okay. All right. Very good. And so if we draw it like this, it's kind of obvious what has to be done, right? So in order for the block to be in equilibrium, i.e. not accelerating, this tension force here, the tension pulling on the block, must be equal to this force here, right? This is the only force pulling the block in the opposite direction. This is pulling one way, this is pulling it the other way. This tension force has to equal this force here, but be opposite in order for the block to be in equilibrium. Right, so because remember, we have a situation like this. You've got the block going up the incline, and it's going through a pulley, and the pulley is, pulling the block down, right? And so this is T here, and this is T there, right? And so what's really pulling this up is mg pulling it down, in a way, right? Right, so what we need to figure out, remember, is what is the mass of the weight, what mass is required to keep this block moving at a constant speed. So really what we can say is m times the force of gravity, the gravitational acceleration needs to equal this piece here. It needs to equal 2,536 newtons. And so we can easily answer that question of what that is. M equals 2,536 newtons divided by 9.8 meters per second squared. And I think what we'll get is 258 kilograms. All right, so if the weight is precisely 258 kilograms, if this thing has a mass of 258 kilograms, it's going to pull this it's going to exert just the right force to pull this thing up at a constant speed. Perfect. Okay. All right. Very good. That will do it for this section. In the next section, we'll do something similar. We'll go through some problems in more detail, but specifically problems involving Newton's second law, not his first law, so instead where particles are in motion, not in equilibrium. All right, until then, take care.